So in the last week, we discussed how given a vector space V and an ordered basis of V, we could associate a column corresponding to every vector. We also saw that if V and W are two vector spaces and if we fix two bases of V and W respectively, then every linear transformation can be associated to a matrix. So we begin this week by discussing how this association depends on the basis. In other words, we would like to see how the column changes, the column representation changes when we change the ordered basis with respect to which we are looking at it, or how the matrix of the transformation changes when we change these bases. So let's begin by considering a vector space V. So let V be a finite dimensional vector space and let beta be an ordered basis. Beta be an ordered basis of V. Let us now consider a new basis beta prime. Let beta prime be another ordered basis. So let us ask the right question. Given a vector V in capital V, we would like to see how are the column representations of V with respect to beta, which we already denoted by V beta is related to the column representation of V with respect to beta prime. This is what we would like to first explore. So in order to study the relationship between V beta and V beta prime, what we will do is we will consider the most natural linear transformation we can think of, which is the identity linear transformation. So to study the above, to study this, consider IV, which is from V to itself, the identity linear transformation. Identity linear transformation. So what we will do is we will consider the domain V with the basis beta. So here let us consider V with the ordered basis beta, and this one is the ordered basis beta prime. This is considered with the ordered basis beta prime. So remember, V and W, we have to fix a basis for V, we have to fix a basis for W, and then we would like to look at the matrix corresponding to these two bases, and that is precisely what we will do here. We would like to see how the matrix of identity with respect to beta and beta prime look like. So consider the matrix IV with respect to beta and beta prime. So let me just give the definition for it, or maybe I will just tell you how they are how this matrix is important, and then let me give you the name of this matrix. So we know that IV of V is equal to V, right? After all, IV is the identity transformation. But think of IV as a linear transformation from V to itself in the above setup, where the domain V is with the basis beta and the codomain or the target V is with the basis beta prime. Then whatever theory we have developed in the last week tells us that IV of V with respect to beta prime, remember this is in the codomain, this is in the range, this is equal to IV beta prime times V beta. IV is after all a linear transformation, right? But what is IV of V? This gives V beta prime is equal to IV beta prime times V beta. We have found out explicitly what the relationship between V beta and V beta prime is. It's related by the matrix multiplication of the matrix IV with respect to beta and beta prime. This matrix, the matrix IV beta prime is called the change of basis matrix. The change of basis matrix from beta to beta prime. So immediately let me give you an exercise or a proposition. IV beta prime is invertible. It's an invertible matrix. Why is this invertible? We have already seen that if we have a linear transformation which is invertible, the matrix corresponding to the linear transformation should also be necessarily be invertible. And we know that identity is an invertible linear transformation, it is the inverse of itself. So, the matrix, the reason is that matrix corresponding to an invertible linear transformation with respect to any basis is invertible. You fix any two bases, and if you look at the matrix of an invertible linear transformation, we have proved that it is invertible. And identity is an invertible linear transformation, and thus IV from beta to beta prime is hence an invertible matrix. Okay, what else can we observe? Observe that IV beta prime is an n cross n matrix where n is the dimension of V. If dimension of V is equal to n, then IV beta prime is an n cross n matrix. You should be able to say more. I'll leave it as an exercise for you to check, or maybe I'll just do it. I'll leave it as an exercise for you to check that the matrix, the change of basis matrix from beta prime to beta is exactly the inverse of the change of basis matrix from beta to beta prime. Moment's thought should give you that. The change of basis matrix IV from beta to beta prime is the inverse of the change of basis matrix IV beta prime to beta from beta prime to beta. Okay, so we have explored how the change of right. So we have explored how the change of basis matrix gives us the relationship between the column vector representation of a vector with respect to beta and the column representation of a vector with respect to beta prime. Let us look at an example. So, an example, let us consider the simplest example, maybe not the simplest, but a simple example. Let us consider V to be just R2 with beta the standard basis E1 which is 1 0 and E2 which is 0 1. The standard basis, and beta prime B and beta prime be the vectors maybe 1 comma 1 and 1 comma minus 1. Let us try to see what the change of basis matrix is. The change of basis matrix is calculated by evaluating what the identity matrix is at E1 and at E2. They will give you the columns with respect to 1 1 and 1 minus 1. So, observe that E1 which is equal to IV of E1 is equal to 1 comma 0, which is equal to half of 1 comma 1 plus half of 1 comma minus 1. So, the first column will just turn out to be half and half. E2 on the other hand, which is equal to IV of E2, which is 0 comma 1, this is equal to half of 1 comma 1 plus minus half of 1 comma minus 1. So, these two calculations tell us that IV of beta of V of identity with respect to beta and beta prime is nothing but 1 by 2, 1 by 2, 1 by 2 minus 1 by 2. That is good. So, let us now see given an arbitrary vector, let us see by brute force how V beta is and what V beta prime is, and also let us see whether they are related in the manner we have just seen. It should of course be the same, but nevertheless let us just have a look at it in brute force. So, let x comma y be some vector in say R2. This is clearly equal to, then there is no confusion on what V beta is, then V beta by the very definition is x comma y. This is after all x times E1 plus y times E2. So, note that V which is equal to x comma y, this is equal to x plus y by 2 times 1 comma 1 plus x minus y by 2 1 comma minus 1. 2x by 2 and 2y by 2. Yes, this is what our x comma y is with respect to 1 1. Oh yeah, right. So, V beta prime is x plus y by 2, x minus y by 2, isn't it? So, one is x comma y. So, if say V is 2 comma 3, V beta will be 2 comma 3 here, and if yeah, v is 2 comma 3, then v beta prime will be 5 by 2 and minus 1 by 2, right. Then if you observe what is IV beta prime times V beta, this is nothing but, recall what IV beta prime is, it's half 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 minus half. This is going to be half 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 minus half. And what was our V beta? V beta was x comma y. This is equal to, you do the calculations, this will turn out to be x plus y by 2 and x minus y by 2, which precisely is our V beta prime, and that is precisely what we have just shown, isn't it? So yes, so this is exactly how the change of basis matrix comes into the picture when we would like to look at how the column vector of V with respect to beta is related to the column vector of V with respect to the beta basis beta prime. All right, now let us consider how the matrix of a linear transformation changes when we change the basis of the given vector space. So, for simplicity, let us do this study for linear transformations from V2 itself. So change of basis matrix and the linear transformations. So, in order to do that, let T, in order to study that, consider a vector space linear transformation from the vector space V2 itself be a linear transformation. Oh, such linear transformations are called linear operators as well. So, I will just note that as well. Linear transformation. Linear transformation V2 itself is called a linear operator. So, let us look at how the matrix of a linear operator changes when we change the basis, ordered basis with respect to which we are looking at the matrix. So, again let us fix a basis, let beta and another basis, let beta and beta prime be ordered basis of V. Consider two different ordered bases of V. Then we have a matrix of T with respect to beta and beta, and there is also a matrix of T with respect to beta prime and itself. So, consider, so let us study how T beta beta and T beta beta prime are related. So, the idea is almost the same. What we will do is we will consider the following. So, let us consider T is a map from V to itself. Again, this is with respect to the basis say beta, and this is with respect to the basis beta. That is what will give you T beta beta. And then let us consider the matrix, sorry, the linear transformation identity. However, the range let us consider with respect to beta prime, and here again let us consider the identity matrix here it is with respect to beta prime. So, what this chain tells us is that IV T IV is equal to identity composed with T composed with identity, it is nothing but our T, right. So, this map. that is also T. But we have developed some notion of how the metrics corresponding to linear transformations behave when we consider compositions. They will just turn out to be the product. So, let us write that down. So, this IV T IV with respect to beta prime this by what we have seen earlier is nothing but IV from beta to beta prime here from here times T beta to beta from here and times IV from beta prime to beta. But this left hand side is nothing but T, because IV is just T, and this is with respect to beta prime and beta prime. So, let Q be the matrix IV from beta to beta prime. Then T beta prime is equal to Q T beta Q inverse. We have already checked, or at least it was given as an exercise, that the change of basis matrix from beta to beta prime is the inverse of the change of basis matrix from beta prime to beta. And if that matrix is Q, then the matrix of T with respect to beta prime is equal to Q times the matrix of T with respect to beta and beta times Q inverse. So, that is precisely how the matrix of a linear operator or a linear transformation from V to itself behaves when we change the basis from beta to beta prime. Such a relationship is given a name, it is called similarity. The not the two matrices A and B are said to be similar if there X is an invertible matrix Q such that A is equal to QB Q inverse. We will see later that such matrices, similar matrices, share a lot of common properties. Therefore, this particular relation that we have just explored is of extreme importance when we study linear algebra further. So, we will see more examples of how linear transformations are the matrix of linear transformations are related to each other through further concrete examples and problems in the problem session.